So, hello everyone. This is our eighth session. I was hoping that more people will join, but since the attendance is low, I think I should start today's session since it's already 3:03. So let's begin today's session. Let me turn the video off. Okay. So basically, one second. So basically, in the previous, what you can say, previous live session, we have solved the problems related to the PN junctions, and we had seen that we had just touched briefly the concept of these hetero PN junction that we can have. We can have P-type material, which will be one kind of a material, and N-type material, which would be other kind of a material. So in this today's live session, we will start with this BJT problem solving session. This will be mostly oriented towards these bipolar junction transistors. So this problem over here, it states that um, we have to consider a BJT which is having some base transport factor, which is given by this alpha t. It is given by alpha t equal to 1 by cos of xb by lb, where this xb is the base width and lb is the minority carrier diffusion length in this base region. Okay, so this alpha t is given to us, and it is has been given to be equal to 1 by cos of xb by lb. So we have been told to find this base width in this PNP BJT. So in order to achieve a transport factor of the order of 0.9967, we have been given this diffusion constant value, and this diffusion constant value, we know this gives us the relative ease, or the measure of the relative ease of the moment of carriers in the presence of concentration gradient. So this dn is given, and this minority carrier lifetime is also given. So minority carrier lifetime is given to us, and this minority carrier lifetime in base is given to us, and also the diffusion constant value is given to us, diffusion coefficient value. So since this is an PNP BJT, what can you comment about the what can I say? Can you comment about the minority carriers? What kind of minority carriers will be in the base? Yes. Okay. So basically, P side will have holes as majority carriers. Okay, and N side will have electrons as majority carriers. Okay, so it means that in this base region, the holes are the minority carriers, and the minority carriers are being injected from the emitter side. Okay, these minority carrier concentration will depend on the injection from the emitter side as well. There will be minority carriers in the base itself, but there will be injection of the carriers from the emitter as well. So in this problem, we have been given this alpha t value, which is 0.9967, 1 by cos hyperbolic cos hyperbolic of xb by lb. So let me calculate this cos inverse of this thing first on the calculator. Okay, so it comes out to be equal to this xb by lb comes out to be equal to 0.0814. Okay, now we need to find this xb, but for that we need to have the value of lb as well. We know that lb is given by this simple relation where this dB is the diffusion coefficient and tau b is the minority carrier lifetime of the carriers. You can check the units as well. It will be satisfying the units of the length, since it is centimeter square per second for dB, and let us check it like this: centimeter square per second, and this carrier lifetime will be having units of centimeter, so this centimeter is a second and second will go, and all this is under the square root, so it would mean that it would be having the units of centimeter. Okay, so this is the diffusion length that we need to find out. This is one simple check to measure whether we are doing the things correctly also, because when we do this simple unit check, you will be seeing that this we will be building some confidence about this lb. We will be saying that yes, whatever we are doing currently is correct mathematically as well. So this dB is having the value of 10. Simply it is 10, and tau b naught is having the value of 10 to the power of minus 7, so it is 10 to the power of minus 6, or its square root will be 10 to the power of minus 3 centimeter. So this is the diffusion length that we will be obtaining. Now for this base width, we will simply say this xb is now lb times this value, which was 0. I guess 0.0814, 0.0814. So it is simply 10 to the power of minus 3 into 0.0814 into 10 to the power of minus 3, or simply it is equal to 0.81 into 10 to the power of minus 6 meters, or simply you can write it to be equal to 0.81 micrometer. So this is the value of this base width that we have been able to calculate. So let's check the options, and option A is the closest to our answer, which was 0.814. So we will go with this point, option A. Okay, now there is some another problem related to this bipolar junction transistor, which is in active mode. It has been given that the base current is 6 microamperes and the collector current is 510 microamperes. Okay, we know that beta is simply the ratio of this IC by IB. Simply this is the IC, where IC is the collector current and IB is the base current. So 510 divided by 6 is simply the value of beta. So if I calculate this thing by calculator, it would simply be 510 divided by 6 is 85. Okay, for alpha is simply for the BJT in this active mode, it is simply beta divided by 1 plus beta. So it is 85 divided by 1 plus 85. So it is approximately equal to 85 divided by 86 is 0.988. Okay, so it's 0.988. Fine. So the value of this problem, it satisfies the option C. Now let's move towards the another short problem, which says that which of the following in BJT is heavily doped region. Okay, which of the following in the BJT is the heavily doped region? And as we all know that emitter is the heavily doped region, because we know that we need to have this thing where the carriers are, since the carriers are coming, all the carriers are coming from the emitter, so it should have high carrier concentration in order to supply those much amount of carriers. So this can be one simple reasoning for this. So this BJT is this emitter for this BJT is heavily doped. Okay. Now this there is another problem, some statement problem regarding this BJT. So it states that which of the following statements is true with regards to the BJT. Okay. One thing is, it says that the base width must be designed much larger than the minority carrier diffusion length. So this statement seems to be false, because if we have base width which is larger than the minority carrier diffusion length, for example, if the minority carriers are the holes in this base region, for example, let's say, so if the base width is larger, the minority carriers will what we can say recombine in the base region, as a result of which we will be having less amount of carriers that are being pumped from the emitter to the collector side. So in order to have more number of carriers that are transmitting or that are being pumped from the emitter to the collector, we need to have this base width which is smaller than the minority carrier diffusion length. This is simply because we do not want to have the recombination in the base region. So that's what we have written it over here. The answer to this question is B, because we need to ensure that we are having very less recombination in the base region of, so that the this reason over here, it states that we know that diffusion length, simply this diffusion length is the average distance which is traveled by the minority carriers, okay, before recombination. Since we want the recombination in the base region to be very low, we want this base to have low recombination. As a result of this thing, we generally design this base width such that it is less than the diffusion length of the minority carriers in order to reduce our recombination chances. So option B for this is the correct. We do not want any recombination of the minority carriers in the base region. We want all the carriers, almost all the carriers, to just get pumped from the emitter to the collector. Okay. Now this you must have seen this what we can say, this transfer characteristic graph, sorry, this output characteristic graph. It says that we are having this early voltage representation. What does this actually represent in the what we can say, in the actual sense? So this early voltage is simply, it is simply a point in on the, what we can say, voltage axis, because whenever we try to extrapolate this curve of these collector currents versus these emitter collector to emitter voltages, we are getting these kind of, we are not completely getting saturated IVs. By saturated I mean that it should have been like this, for example. the complete saturation should have occurred, for example. But since we are getting the curves to be like this, this means that it has some resistance associated with it. Okay, so since it has some resistance associated with it, we try to extrapolate these these collector current values, and we observe that they intersect for different VBEs. If this is the increasing VBE, we observe that they intersect this collector to emitter voltage axis at some particular negative voltage value, which is represented or named by the name of early voltage. So this VA is the early voltage. So this curve, it does not represent the breakdown at the junctions. For example, if breakdown would have occurred, so if breakdown would have occurred, it would have meant, for example, if I am having a current curve like this, which is trying to saturate, and then abruptly I am having some current which is increasing. Okay, if this is some VC, this is IC, this would have meant breakdown. Okay, since the characteristic is not like this, it is not the breakdown current. Okay, the saturation, okay, sorry, the saturation begins, the option B, it says that the saturation of the collector current begins. By saturation we mean that, for example, if I am having this some current IC with this some VC, it would have meant that the saturation begins at this point. Okay, but since these curves are not saturating, so this statement also is wrong. This statement C says that curves on collector current characteristic intersect the voltage axis, and when extrapolated to zero collector current value, this is what it means. So it simply means that we are finding or looking for the point where this collector current will be zero at a particular collector to emitter voltage. So option C is the correct option to go with. Now, as I was saying previously, this this is having some resistance associated with it. This for the BJT in active mode, forward active mode, when we are having this curve of these different collector currents with respect to different the collector to emitter voltage for different VBE voltages, that is base to emitter voltages, we will be actually having this transition, not the transition, we'll actually having this slope in the characteristics. So this slope is simply anything, for example, if I am having this V, some voltage, V is voltage, and from the Ohm's law we know that V is equal to IR. So this there is this relation between this voltage and current, and this is denoted by the proportionality constant, which is known by the name of resistance. Okay, so if this if we are having some IV curve, then if this IV this current curve is having some slope with respect to this voltage, it simply means that the that this characteristic or this current voltage relationship is having some resistance associated with it. So it means that this it has been written over here that, as it's clear from the figure, that the output conductance is simply slope, and it is given by slope is 1 by R naught, and this R naught is the output resistance. Okay, so as the base width modulation increases, the slope of IC, this collector current, with this VCE will increase. Okay, hence the output conductance will increase. Okay, so it's as simple as that. So this base width modulation results in the increase in the slope, or will result in the increase in the slope of IC versus this VCE, collector to emitter voltage, and as a result of this, this conductance will increase, or the resistance is the opposite of the conductance, or the resistance will decrease. So as is evident from these curves that the slope is increasing. You can see the slope is increasing. The slope is increasing as the value is as this is increasing. So base width modulation results in the increase in the output conductance of the device. It should be D here. Okay. Now we have another problem, but this time this is some mathematical problem. Till now we were having these what you can say, these statement kind of problems. So it says that uh, we are having a uniformly doped BJT, silicon BJT, which is having the following specifications. Specifications have been given to us. The base doping is the base width, first of all, is 0.5 micrometer, and the base doping is 10 to the power of 16 centimeter cube. Okay. So the punch through voltage has been given to us. It is 25 volts, and this built-in voltage VBI is much less than this 25. What I can say, 25 volts. This punch through voltage. So we have been told to find the collector doping concentration from this what you can say, from this problem statement. Okay, so we have to find the collector doping concentration. So it simply means that if I draw the emitter, base and collector region, for example, it would look like this. If this is my this BJT, this is the, for example, this is my interface of this emitter and base. Okay, so it would be, this would be, let's denote it by x1, let's denote it by x2. This whole thing is the base width WB, and this is the collector of ours. So let's consider this x1 is this space charge region, or the depletion charge region that's extending into the base. Okay, WB is the metallurgical base width, which is given to us to be equal to 0.5 micrometer. We know that this x1 is simply, this depletion width is simply 2 times epsilon naught epsilon r VBI plus VR, where this VR is the this bias, reverse bias applied to the junction. So this is NC by NB divided by NC plus NB. So x1 is for this case, particular case, this applied voltage over here, this is VR is equal to V punch through voltage. Okay, so it is equal to 25 volts, and also it has been told that this VBI is much less than 25 volts, and this x1 we have to assume, since we have to assume this punch through, we are assuming the condition that the punch through has occurred. As a result of this thing, we will say that x1 is equal to, approximately equal to the what we can say, metallurgical base width. We have considered the punch through case in this problem. So this would mean that it would simplify this relation to this x1 becomes WB square 2 times epsilon naught epsilon s divided by Q, yes, VVR NC divided by, sorry, NC divided by NC plus NB into NB. So this we need to find the value of NC. So this NC, I would rather say this, it is equal to this NC is simply equal to WB square. WB square is 0.5 micrometer. It is 0.5 into 10 raised power minus 6 meter, or you can simply say it in, use it in centimeters. So it is 0.5 into 10 to the power of minus 4 centimeter. We need to square this thing. This is equal to 2 times epsilon naught into, it is 8.854 into 10 to the power minus 12 into this thing. Since it's silicon, it is 11.7, VBR is 25, Q is 1.6 into 10 raised power minus 19. This NC, it is NC plus NB. NC plus NB is simply equal to 10 to the power of 16. Okay, it is equal to 10 to the power of 16 times this value. This is equal to 10 to the power of NB is equal to 10 to the power of 16. Okay, so let's try to solve this first. So this whole thing is multiplied by NC. So it would mean that we are left with 0.5 into 0.5 is 0.25. So it's 0.25 into 10 to the power of minus 8. 0.5, 0.25 into 10 to the power of minus 8. Okay, centimeter square. And this is 10 to the power of minus 14, sorry, because I am dealing in a farad per centimeter square. Okay, so let's basically solve this. 2 into 8.85 into 11.7 into 25. Okay, it comes out to be equal to 5.177 into 10 to the power of 3. So it is 10 to the power of minus 11. This thing is 1.6 into 10 to the power of minus 3 times the NC. So this whole thing, NC plus NB, okay, this is the value we will be getting. So I guess it is coming out to be equal to, this whole thing is 10 to the power of 0.25 into 1.6 is simply, let me check this, 0.25 into 1.6 is 0.4. 0.4 into 10 to the power of minus 11 is equal to 5.177 into 10 to the power of minus 11 NC divided by NC plus 10 to the power of 16. So 10 to the power minus 11 and 10 to the power minus 11 will go. It would be 0.4 NC plus 0.4 into 10 to the power of 16 into NC into 5.177. Okay, so basically it's quite tedious calculation. I shouldn't have done this. So it is 5.177 minus 0.4, which is 4.77 NC is equal to 0.4 into 10 to the power of 16. Okay, 0.4 divided by 4.77 is simply equal to, it gives me this value to be equal to 0.083 into 10 raised power 16, or simply it is equal to 8.385 into 10 raised power 14 centimeter cube. Okay, let's check the options. Option A, I guess, is matching with our results, so we will go with option A. Now we are required to find the depletion width of this collector once the punch through has occurred. So it would simply be equal to, this x2 will simply be equal to 2 times epsilon naught epsilon r VBI plus this V punch through voltage divided by Q NB NC 1 by NC plus NB. Okay, so let's not solve this because it's simply doing the previous problem mathematically again. So let's leave this. Let's move towards another problem which says that we have to consider a uniformly doped PNP BJT, sorry, NPN BJT, and with the following specifications. Like, the bias is given to us, it has been given that this PNP, sorry, NPN BJT is in forward active mode, and the collector to base voltage is given to be 3 volts, and the base width, metallurgical base width, is given to be equal to 1.1 micrometer, and as expected the doping levels are of the range that emitter is having the highest doping, followed by the base and then the collector. So we have been told to determine the base to emitter voltage such that the minority carrier concentration at x equal to 0 is 10% of the majority carrier concentration, majority carrier whole concentration. Okay, so it means that this we need to find this first of all we need to find the this what we can say, this electron minority carrier concentration of these. Okay, minority carrier concentration of these electrons in the uh, p p side, what we can say, or p junction. Okay, so if np naught is the equilibrium minority carrier concentration of the holes of the sorry of this so we will find this by simply using the uh, law of mass action. Wait a second. Okay, law of mass action, Ni square is by Nb. So it would simply mean, since this Nb is having this base is having the concentration of 10 to the power of 16 of what we can say holes, so the minority carrier concentration would simply be, for these electrons, would simply be given by Ni square. Ni is 1.5 into 10 to the power of 10 whole squared divided by the concentration of the holes in the P region, which is 10 to the power of 6. We have assumed complete ionization. Let's keep that in mind. So it is 2.25 into 10 to the power of 20 divided by 10 to the power of 16, which is 2.25 into 10 to the power of 4 centimeter cube, which is the minority carrier, equilibrium minority carrier concentration. Now, as a function of position, it would be this. Since we need to find it at x equal to 0, let's write it simply. This minority carrier concentration as this minority carrier concentration is simply given by the equilibrium concentration times the exponential of the base to emitter applied voltage divided by the Vt, which is the Kt by Q, our thermal voltage. Okay, so if I take the ln on both sides, it would simply be VBE is equal to Vt ln of Np0 divided by Np naught. Now Np0, Np at 0 has been given to be equal to, we have been told that the minority carrier concentration at x equal to 0 is 10% of majority carrier whole concentration. 10% of majority whole carrier concentration is 10 to the power of 16. So 10% of this 10 to the power of 16 is the minority carrier concentration at the at x equal to 0. So it means that it is equal to 10% of 10 to the power of 16 is simply 0.1 into 10 to the power of 16, which is 10 to the power of 15 centimeter cube. So VBE is simply, VT is 26 millivolts, okay, and NP naught is 10 to the power of 15, and NP0 was 2.25 into 10 to the power of 4. Okay, so let's solve this. It would simply be 10 divided by 2.25, 10 divided by 2.25, which is 4.44, which is 4.44 ln of 4.44 into 10 to the power of 10 into 26 divided by 1000. So it comes out to be equal to 0.637. Okay, it comes out to be equal to 0.637 volts. So this is the value of the base to emitter voltage that we will be requiring. Okay, let's check the options. Okay, I think 0.635, yes, 0.637. I think option A is the closest option to our answer. So since it is 0.635 and ours was 0.637, so option A is the correct option to go with. Now changing the directions and moving towards the MOS cap. So as we know this MOS cap, you must have heard MOS cap every time whenever you are doing this semiconductor device physics course. You must have heard that this is the heart of the semiconductor, and the MOSFET, whenever you start with the MOSFET, you first just get insights into the MOS cap, because this MOS cap is simply what we can say fundamental building block of that MOSFET. You must have heard the statement that this it is the simplest device, and also it is the heart of the all the metal oxide semiconductor based devices. So what this MOSFET, or sorry, MOS cap simply consists of, it consists of a, let me draw its what we can say what is a schematic. So this MOS cap, sorry, it simply is like this. If this is the silicon, okay, this is our silicon, let me draw it like this, so that it is, this is our silicon, this is our oxide, okay, SiO2. So basically it will be having some metal over it. Let me denote it by this thing. This is the metal which is having some contact over it, which is Vg, let's say, since this is gate, and we will be having the this is simply metal, oxide and semiconductor. So this is the R MOS, simply MOS cap. So basically it consists of this what we can say silicon dioxide layer or the oxide layer, which is between sand or sandwiched between this gate, which is metallic in nature, and the this silicon substrate. Okay, silicon substrate. Oh, so this also has this metallic, or we can say layer, which is present at this bottom of this MOS cap. Let me draw it like this. It would be this metallic layer which is below this MOS cap. So this provides this contact to the silicon substrate, this Si. Okay, this is grounded. Okay, this is grounded, and this is normally grounded. Let's say this is normally grounded. Okay, so it is if we consider now this ideal what we can say ideal MOS cap structure, it would be having some what we can say it would be having some I would rather say it would be having some extraordinary properties that we are going to require. For example, we are assuming for the ideal MOS cap this metallic gate is there, and we are assuming that this oxide is perfectly insulator, and we are saying that this oxide is having no charges inside it. I am talking about the ideal MOS cap first. So there are some basic assumptions for this ideal MOS cap, and one among those is that this metal work function is equal to semiconductor work function. Okay, phi ms is 0. So this is for ideal MOS cap. Okay, so it would mean that this ideal MOS structure will be having this semiconductor work function is simply sum of the electron affinity plus the difference between the conduction band and the Fermi level. So this is the metal work function or the semiconductor work function for the ideal MOS cap structure. Okay, we all know that if we have to understand any device, for example, we need to have its basic representation of the, for example, of the energy band diagrams. So this energy band diagram, it enables or it gives us the insights how the device will behave, particularly at the interface, because the interface is the main thing. All the device physics that is occurring, it happens at the interface. So if now we try to build on this concept, and we try to consider a specific case. I know that you might have studied this thing in the lecture. You must have seen that this you have taken this silicon to be as p-type substrate. Okay, you had taken this silicon to be as p-type substrate, mostly what it is done. So in here we will consider n-type silicon substrate. Okay, so if we will consider this n-type silicon substrate, we will try to what I can say draw its energy band diagrams. So when there is nothing and we are assuming the flat band conditions, the metal side we are assuming all the idealities. Okay, the metal work function is equal to semiconductor work function, and there is no charge inside the oxide, all the assumptions that I told you previously. So if that is the case, this energy band diagram for this n-type n-type material would simply look like this. This is the metal side, okay. This is the oxide side, okay. And since this is an n-type material, it would be having this Fermi somewhere here. Since this is n-type material, this will be intrinsic Fermi level, okay. This will be the conduction band edge. This will be the valence band edge. So this is the condition when we have Vg or gate voltage equal to 0 and phi m is equal to phi s, comma, no charges in the oxide, okay, in the oxide. So these are some simple assumptions that we are taking, okay. So remember, this is the n-type substrate. Whatever I have drawn over here, silicon can be doped n-type or p-type. The case we have taken is for the n-type. So this is n-type silicon substrate, okay. Now let's draw the energy band diagrams for the various biasing conditions, okay. It would help us to build on the concept of the what I can say about the how the device physics changes with the different or can say different biasing conditions. I wouldn't say device physics. I would say physics that is related to the interface, okay, how it responds to the gate biases, okay, the external gate biases. So if now we consider this this gate voltage, if this gate voltage is positive, okay, if gate voltage is, if gate is positively biased, okay, it would mean that this Vg is greater than 0 and there will be this Fermi level shifting, okay. The Fermi level in this metal side will be lower than the Fermi level in the semiconductor, okay. This would result in the slope in the energy bands in both the insulator and the semiconductor. For example, if I draw the energy band diagram again for this case, it would look like something like this. Since I have applied positive bias, at gate, Vg is positive at gate, as a result of this thing I will be having accumulation of electrons. Yes, I will be having accumulation of electrons because electrons are the majority carriers in n-type material. We will be having lot of electrons that can easily move towards the interface. As a result of this thing, the interface will become more n-type, okay. That is simple because I am applying positive bias. I will be attracting the negative charge towards the interface, okay. As a result of this thing, we will be having electrons that will come closer to the interface. So if this is our metal side and I am applying some Vg which is positive Vg means since this inner energy is related to this applied bias by minus times the V voltage applied, or minus E is equal to minus QV simply. So as a result of this thing, the metal side Fermi level will be lower with respect to the Fermi level of the semiconductor side, okay. Now this is the metal side, this will be the oxide band bending, and this will be our the metal and this will be our the semiconductor side, okay. This is the semiconductor. For example, let me draw its Fermi first. Fermi level will remain constant throughout, okay. So the intrinsic Fermi level will have the band bending same as the valence band, and since the surface interface has now become more n-type, more, what I can say, n-type. As a result of this thing, the band bending near the interface is towards the Fermi level. You can clearly see, since this EC minus EF at interface is less than EC minus EF in the bulk, this means that interface is more n-type. Okay, so this case is for the accumulation. Let's remember, let's bring it to our notice again that this is n-type substrate. Okay, this is n-type substrate, and this is now the accumulation. Whenever we are applying the positive bias to this thing, to this metal, the electrons will be attracted to the oxide semiconductor interface, and as a result of this thing, we will be having the build up of the electrons at the interface. So the majority carrier now concentration is now greater than the, what we have seen said, that majority carrier concentration is greater near the oxide semiconductor interface. It oxide is, that is the interface is more n-type, or other ways we can say that majority carrier concentration is more near oxide semiconductor interface than bulk. Okay, so this is the major statement about this material in under this biasing condition. Now if this voltage is now negative voltage is being applied to this material, for example this gate, as a result of this thing, we will be having, for example, I am applying the small negative voltage, small Vg, but Vg is less than 0. Okay, though, so since this Vg is what I can say, Vg is less than 0, EF of metal will rise with respect to the Fermi of the with respect to the Fermi of the semiconductor, EF of semiconductor. Okay, semiconductor. Now it means that this small increment in the Vg would result in the slope, again it would result in the slope of the energy band diagrams in both of the insulators and the semiconductors. As a result of this thing, it is simply that since Vg is negative and we are applying it to the gate, this results in the electrons which are majority carriers in the n-type substrate. This results in the repelling of the electrons near the interface, and as a result of this, positively donor sites will be exposed to our what we can say biasing conditions. This means that this biasing condition results in the depletion of the electrons from the interface. So this electrons basically this electrons over here, it simply means that I have applied some negative bias. As a result of this thing, since I have applied some negative bias, and this thing results in the this building of the positive charges near the what you can say semiconductor metal interface, semiconductor oxide interface. So as a result of this thing, the surface will be interface will be less N type. So it would look like this. Okay, it would look like this if this is the Fermi of the semiconductor, and this is the intrinsic Fermi level. Okay, this is the conduction band edge, this is the valence band. So it simply means that this metal oxide and semiconductor, okay, this has now, this interface is now having a, more what we can say, concentration of holes as previously. So it has been, since it has been depleted due to this negative bias, we have applied negative bias, which resulted in the repulsion of the electrons from the interface and exposed those positively donor sites, charged donor sites, and this resulted in the band bending or the developing of the positively charged carriers at the interface. So this condition is known by the name of depletion. Okay, it is known by the name of depletion because we are depleting the majority carriers. Okay, majority carriers were electrons in this case, and since we have applied the negative voltage at the gate terminal, as a result of this thing, we will be having the uh, positive charge build up, which is due to these what we can say, these donor sites, and this results in the band bending towards the what we can say, band bending in the semiconductor interface, with uh, uh, with this condition being that the material is in depletion region, and since now the bias is low, this bias can be increased or enhanced. As a result of this thing, the material can become very much p-type at the interface. So when we increase the bias, when we increase it to a large negative bias, for example, this will increase the negative charge obviously in the on the gate. As a result of this thing, more holes will be generated, or there will be more hole concentration, and this will result in this band bending, and this Fermi level will intrinsic Fermi level will just what we can say, bend that much that it would be very close to the uh, what you can say, this Fermi level. For example, let me draw it. When I am saying that I am applying large Vg less than 0, so it would mean that I will be having large slope compared to the previous case. Since I have applied Vg very negative, the relative motion of this Fermi level on the metal side would mean that the Fermi level has gone up relatively relative to the Fermi level of this semiconductor side, and semiconductor side will remain, the Fermi level would remain constant throughout, but at the interface the intrinsic Fermi level will behave like this, because the charge buildup of the positive carriers, and we will be having the interfaces very much p-type, and this condition is known by the name of inversion, and for n-type it occurs at some bias which is Vg less than V threshold. Okay, V threshold, this is some threshold voltage. So basically the whole concentration has increased such that they now it is greater than the electronic concentration that was present at the surface. So it has been named as this term has been named by the inversion name. So basically the when Vg is less than this threshold voltage, the minority carrier, this minority carrier at this interface, this minority carrier concentration, rather I would say minority carrier concentration at the interface, will be much greater than majority carrier concentration in the bulk. So this is simply the definition of the inversion. Okay, the minority carrier concentration at the interface will be much greater than the majority carrier concentration in the bulk. So we have seen all the cases, what I can say for this MOSCAP, although we didn't go into that much detail, but still for the N-type substrate we have seen that how the capacitances, how these values would change, these band bendings would change with the applied bias, and as a result of this thing we will be having different regions of operation. One would be, for example, considering an ideal MOS, one would be corresponding to the flat band condition having phi m equal to phi s with no charges inside the oxide, and another would be that we will be having this Vg which is greater than 0, resulting in the accumulation of the carriers. In the N-type case it was the electrons, and that was the accumulation case. Then we tried to deplete the carriers at the interface by applying small negative bias. This resulted in the uncovering, or the, what you can say, on the or the exposing those positively charged ions at the charged donor sites at the interface. And then the third case was of the inversion, when we had a large negative bias applied to the gate. As a result of this thing, we have the onset of inversion. We had the inversion where the minority carrier concentration was much greater compared to the majority carrier concentration of the bulk, and all these things are happening at the interface of the oxide and the semiconductor. Okay, so this is one thing regarding this metal oxide semiconductor. We can do this for the p-type as well, p-type substrate as well, and I hope that you have seen that this for p-type as well. So we can just draw a schematic, or this we can say representation of these plots, where we would simply say how it depends on the bias for N-type and the p-type substrate. Okay, for if this is the Vg scale, for example, if this is the Vg scale, this is Vg is the gate bias, and this is N-type, for example, substrate, then we have seen, for example, if this is our 0 axis, okay, we have seen there will be accumulation considering the ideal scenario. Okay, we have to consider the ideal scenario. We have seen that when the bias was positive, there was accumulation of the charge carriers. Then up to some voltage we had this depletion, and this depletion region was up to some particular threshold voltage, and after that we had this inversion region. When this bias was significantly large negative, we saw that we had the onset of the inversion. Then for large negative it was the inversion region only. Okay, and for the p-type, reverse thing will happen. Okay, for the p-type, a large negative bias would mean that we will be having accumulation of holes, obviously, So a large negative would mean we will be having accumulation of holes at the interface. Okay, a small Vg would mean we will be having the depletion of carriers at the interface up to a particular threshold voltage, and after that when the inversion this onset of inversion has occurred, and we are applying more positive bias to this p type, we will be having the inversion of the at the interface. So a large negative in the case of p type would mean accumulation. This is p type substrate. Okay, n type substrate, and this is p type substrate. So these are some of the what you can say insights into the how the different kind of substrates, silicon substrates, would help us to achieve different kind of behaviors at the interface depending on the biasing conditions. Okay, now we can move towards the capacitance part of this thing. We can say that this also, let me say that this gate voltage, whenever I am applying some gate voltage Vg, it drops into two things. One is the oxide and another is the semiconductor. So in here we are considering that there is no drop in across the what you can say bulk semiconductor. Okay, we are considering the drop across the bulk semiconductor to be zero. So remember, whenever I am applying the bias, it is getting what you can say, it is getting divided into two portions. One is the oxide, across the oxide, and another is the semiconductor. Okay, remember this thing. This will help us to solve some of the problems while going forward. This is basically, simply you can say, it is the energy or voltage conservation. Energy conservation is simply voltage conservation, or KVL, or whatever you would like to say. Okay, so now from this I think we should move to the capacitances. So this capacitance, you must have seen that this capacitance is having this kind of a behavior where if I consider this p-type substrate, now let's focus on the p-type substrate mostly now. So if I'm having this p-type substrate, you must have seen for this MOS cap, you will be getting CV some kind of this thing. This, if this is the considering the idealities, everything is ideal, for example, it would be like this. Okay, this shouldn't be like this, it should be like this. Okay, this is for low frequency. Okay, this is for high frequency. So this is capacitance, this is voltage, and the substrate is p type. Okay, this is all related to the what I can say, all related to the biasing conditions that we earlier saw. We said that in the accumulation region, we will be when we will be having this large bias, large or some negative bias applied. As a result of this thing, we will be having this accumulation of the positive carriers at the interface of the oxide and the semiconductor. So this would result simply in the accumulation of the positive majority carriers, which in this case is the holes. So this basically this capacitance measurement, whenever you see, it is done by applying a small, what I can say, a small uh, AC signal. Okay, and we are changing we apply this small signal, and we change the gate bias. Okay, we change the gate bias. This is VG. We change the VG. We change the VG from accumulation to depletion to inversion. Okay, this is what we do. First of all, we apply a small AC signal and we change the gate voltage, or this what I can say, a DC bias conditions from the accumulation to the depletion, then go move on to the inversion. So basically this accumulation, there will be majority carrier concentration. This accumulation will be having majority, okay, majority carrier concentration build up. Okay, it would be associated, this accumulation would be associated with the majority carrier concentration build up at this oxide semiconductor interface. Okay, so this since this is associated with the majority carriers, it would change rapidly, because the majority carriers are already in a large number. So whenever I am applying this DC bias, these majority carriers, they will respond quite easily to the applied biasing conditions. So this results in this results that if I am applying some AC signal upon this, for example, this system that I am trying to measure, it would result in the adding some, for example, charge to the to this, for example, interface on the metal side and the interface on the semiconductor side, but this would be very small as compared to the what we can say, the charge concentration or the charge which is present already on the interfaces lying at the metal and the semiconductor side. So this simply makes our structure a simple parallel plate capacitor. So it simply means that this, under this accumulation, the majority carrier concentration build up is very fast, and as a result of this thing, we will be having simple parallel plate capacitor in the accumulation region. So it means that this accumulation region would be having the capacitance value which would be close to 1 if I consider it to be C by Cox. Okay, if I consider it to be equal to C by Cox, okay, this will be ideally 1. It will be close to the value of oxide capacitance. Okay, this will be Cox. Now when we are applying some this positive bias in case of PP type substrate, we will be doing the depletion kind of a thing that we have seen previously. So whenever we are trying to deplete the carriers, so it would mean that it would change my what I can say, depletion width or the depletion layer region, which is related to this majority carrier withdrawal. In this case, since I am applying positive bias, I will be repelling these p-type majority carriers, that is holes, and I will be attracting electrons towards the interface. So the majority carriers are now applied and associated with this kind of a operation, and they also can change very rapidly inside this depletion region. But when we apply this what I can say, this DC this AC bias over it, we will see that this this results in the negative charge, for example, on the this gate side, and this depletion region widens a bit, and So when this thing is happening, we are having depletion capacitance as well. So two capacitances are coming to us, which are basically in series. So basically we are having two kind of capacitances which are coming to us. We are having the oxide capacitance and we are having the semiconductor capacitance. So that is coming to our rescue. So this means that the value of this there is this dip what you are seeing over this region over here. It is associated with the depletion region. And now when this inversion is again happening, when this inversion is happening, it would depend on the recombination and generation of the, for example, carriers, minority carriers. Because if I am applying high frequency, I am not giving a large or enough time for the generation and recombination process. So it would mean the generation process is, for example, slow when I am applying high frequency. So the material will respond in such a way that the capacitance will be fixed at this depletion capacitance value. But if I am giving this low frequency, I am giving enough time for the generation and the recombination of carriers. As a result of this thing, at low frequency I will be having the generation of these minority generation and recombination of these minority carriers in response to the AC signal, because the AC signal in our case is now having low frequency. So this results in the characteristics which are looking like this, because the capacitance will now tend to the what I can say towards the uh, uh, oxide capacitance again. Okay, so this is all about this thing, that how we have been able to move from the region of the accumulation to the depletion, and then to the again to the inversion region. And we have seen two cases for this inversion region, where we will be having high frequency region which will correspond to the CV curve with this value of oxide capacitance close to this depletion capacitance value. And then we will be having this another case which is corresponds to the low frequency value, where we will be having enough generation and recombination of the magnetic carriers, and as a result of which we will be having the oxide this capacitance by this capacitance tending to the oxide capacitance, and as a result of this thing we will be having the ratio to be equal to 1, the C by C ox to be equal to simply equal to 1. Now let's move towards some problems related to uh, this what I can say MOSCAP. You can simply say that since this is the MOSCAP was the, as we said, that this is the heart of the semiconductor device physics, and that's why we try to spend a bit time on its understanding of how the charges or how this the charges pile up, or how the charges are building at the, in my this metal oxide oxide semiconductor interface. So now from that we will try to infer some mathematical problems, mathematical results that are basically related to the physical aspects of the oxide semiconductor interface. Now it says that this we have to consider a MOSCAP with a p-type silicon substrate, and this p-type silicon substrate has been doped to a carrier concentration of 3 into 10 to the power of 16 centimeter cube. The work function is given to be equal to minus 1.13. So it is not ideal MOSCAP. Okay, so It simply means you must have gone through this in the lecture. It simply means that we have to find this threshold voltage, and this threshold voltage is simply given by phi ms plus 2 phi fp. This 2 phi fp is the Fermi pinning potential that we are considering, plus q times the maximum depletion charge divided by the C ops. Okay. Now for the phi fp, we need to find it by the doping carrier concentrations. Phi fp is simply Vt ln of Na by Ni. It is 0.026. Ln of Na is 3 into 10 raised power 16. Ni is 1.5 into 10 raised power 10. So it is simply 2 into 10 raised power 5 in ln. So it means that ln of it would be 2 into 10 raised power of 6. 2 into 10 raised power of 6 into 0.026. So it is 0.377. So it is 0.376. Sorry, 76. 0.376 volts. This is the value of the phi fp. Now for the maximum charge, it would correspond to the depletion width, maximum depletion width. So for this to be maximum, it is simply given by q and a into xd. Xd is the maximum depletion width, and it is given simply by 2 times epsilon s. We have considered the this Fermi level pinning to happen at 2 phi fp, and this is given by q na, 2 epsilon s phi s by q na. So it is simply 2 into 2 is 4, epsilon s is 11.7 into 8.85 into 10 raised power minus 14. Phi fp, we found out it was equal to 0.376 by qna is 1.6 into 10 raised power minus 19 into the na. Na was 3 into 10 to the power of 16. Na is 3 into 10 to the power of 16. All this thing under the square root. So basically it is large calculation. 4 into 11.7 into 8.85 into 0.376 divided by 3 divided by 1.6. It is 32.444 into, it is 10 raised power minus 14. It is 10 raised power minus 20, 10 raised power minus 11. Okay, it's 10 raised power minus 11 simply. So let us take its square root. Root of 324.4. It is approximately equal to 18 into 10 raised power minus 6 centimeter. This is a depletion width, or simply it would be equal to 0.18 into 10 raised power minus 6 meter or micrometer. So this is depletion width. Okay, so from this we can find this maximum depletion charge, which would be q times na into xd. So it would be simply Q times Na into XD. It is simply 1.6 into 10 raised power minus 19 into Na. Na is 3 into 10 raised power 16. 3 into 10 raised power 16. Xt is 0.18. 0.18 into 10 raised power of minus 4. Let's do it all in centimeters. Okay, so it would come out to be equal to 10 raised power minus 23 plus 10 raised power 16. It would mean raised power of minus 9 into 1.6 into 3 into 0.18 is 0.864. It is 8.64 into 10 raised power of minus 8 coulomb per centimeter square. Now this Vt threshold voltage is given to be equal to 0.65. Vt is 0.65. Okay, and this phi ms is minus 1.13. Phi ms is minus 1.13. So Vt is equal to 0.65 is equal to minus 1.13 plus 2 times phi of p. Phi of p is 0.376. 0.376 plus q depth is simply 8.64 into 10 raised per minus 8 coulomb per centimeter square. C ox is simply epsilon ox into T ox. Epsilon ox by T ox, sorry. So it is epsilon ox, epsilon ox into T ox. So it simply means that 0.65 plus 1.13 minus 2 into 0.376 is 1.028. 1.028. 8.64 into 10 raised power minus 8. Epsilon ox is simply 3.9 into 8.854 into 10 raised power minus 14 is equal to into T ox. Okay, so let us basically add another slide for this. So it would mean 1.025 into 3.9 into 8.854 divided by 8.64 is 4.11 into 10 raised power of minus a 6 centimeter. Okay, so it comes out to be equal to this T ox value comes out to be equal to 4.11 into 10 to the power of minus 6. It is minus 14 into 10 to the power of minus 6 centimeter. Okay, or simply it is 4.11 into 10 to the power of minus 8 meter, or let's see what units we are required to find it in. So the determine it is in nanometer. Okay, we need to find it in nanometer. So it is 4.11. It is 41.1 into 10 raised power minus 9 meter, or 41.1 nanometer. This is the thickness of the oxide that we will be requiring. So the option B is closest. It is 41 nanometer, and our answer was 41.11. So the option so for the option B seems to be the correct for this question. So we will select the option B. Now let's move towards another problem. This from this curve you can easily say that this is the MOSFET when we are having the AC signal of high frequency. Clearly, because this is not going again to the value of the oxide capacitance. So since the frequency of the signal is very high, they have generation and recombination mechanism, which is already a slow process, will not be able to catch up with this high frequency, and as a result of this thing we will be having this capacitance limited to the depletion capacitance value itself. So it says that this figure shows the high frequency capacitance voltage characteristics of metal silicon dioxide silicon MOSFET having an area of 1.1 having an area of 1 into 10 raised per minus 4 centimeter square, and then we are given that the permittivity values of the silicon and silicon dioxide, and we have to find the maximum depletion width in the silicon. So clearly when let us solve it by considering the previous studies that we have seen in the previous what I can say previous half an hour, when this for example when bias is 0 volt, clearly there is, if I see this 0 volt, clearly there is no depletion. Okay, there is no depletion, hence we will be having only one capacitance capacitance only one capacitance, which is the this oxide capacitance. Okay, this oxide capacitance is simply equal to now the 7 picofarad. Okay, now this if we are applying some voltage and the depletion region is being formed, we will be having some capacitance associated with this device, which will be simply given by 1 by C total, which is equal to the series combination of the 1 by C1, which will be the oxide capacitance, plus the 1 by C2, which would be the depletion capacitance simply. Okay, so if I now I know this C total value, C total is equal to 1 picofarad. Clearly C total is equal to 1 picofarad. Okay, so it would mean that this this C total is simply equal to C1 into C2 divided by C1 plus C2, and this is equal to 1 picofarad. Let us not write picofarad because we can get the value of C2 in the picofarad itself, and C1 was equal to 7 picofarad into C2 divided by C1 plus C2. So it is simply 7 plus C2 is equal to 7 C2, or 7 by 6 is equal to C2. So value of this depletion capacitance is simply 7 by 6 picofarad. Okay, now we can simply find its what we are required to find. We have to find the maximum depletion width in this silicon. This we know this capacitance is simply this depletion capacitance or any capacitance simply given by epsilon naught A by D. Okay, so if this is the silicon dioxide, since this is the silicon dioxide, we need to find its this epsilon naught into epsilon R So this, since this is the silicon dioxide in conjunction with the silicon, and the depletion capacitance, remember, since the depletion capacitance, it is associated with the silicon, okay, so the relative permittivity of the silicon will matter to us, okay. So this epsilon naught in this case is epsilon s simply, okay, because the depletion capacitance is in the semiconductor region, epsilon s a by this d over here is the depletion width in the silicon region, which is denoted by xt, okay. So this epsilon s is simply 10 to the power of minus 12, and area is simply equal to 10 to the power of minus 4, and this xd we need to find it simply. So this xd is simply 10 to the power of minus 16 divided by C2, or this is 6 into 10 to the power of minus 16 divided by 7. Pico means 10 to the power of minus 12, okay. So it means 10 to the power of minus 4, 6 by 7. So it simply means 6 divided by 7, okay, which is 0.857, 0.857 into 10 to the power of minus 4, okay. So it is simply 0.857 centimeter or 0.857 micrometer, okay. So basically we have found out the depletion width from just calculating, or from just looking into the CV characteristic of this MOSFET. We've observed that this MOSFET is under the different biasing conditions, and we observed that how this MOSFET will behave under the different biasing conditions, with depletion region uh, being identified by this, what I can say, by this uh, hump, or what I should say hump, by this transition over here, and then the inversion region, since this is this signal applied, the AC signal applied to this case is a high frequency AC signal, and as a result of this thing we won't be having enough recombination and generation in of the carriers, of the minority carriers. As a result of this thing we will be having very uh, sorry, as a result of this thing we will be having this pinning of this capacitance value to this depletion capacitance, or this depletion capacitance itself. So this resulted in the some depletion, maximum depletion width corresponding to the particular what we can say particular thickness of the for this depletion width, and this resulted in the value to be equal to 0.857. So we saw that in this accumulation region we just had only the oxide capacitance, while as in the depletion region we had this semiconductor capacitance, which was the predominantly this depletion capacitance. We had the series combination of this oxide capacitance and the depletion capacitance, and as a result of this thing we are able to solve this series combination, and we got the value for this xt to be equal to 0.857. So 0.857 value is the correct option. Now we have another problem which is related to this MOSFET. It says that this MOSFET, again it is the p-type silicon substrate. We have in this lecture we previously saw that we can use the n-type substrate and how we can solve for it, and how we can obtain the different interface band bendings. And this simple case over here is for the p-type silicon substrate, which has been doped to up to the concentration of 10 to the power of 16, and the oxide is silicon dioxide with the thickness of 55 nanometer, with device area equal to 2 into 10 raised power minus 3 centimeter square, and we have been told to calculate the value of the oxide capacitance, total oxide capacitance. So it is simple. So since this oxide capacitance per unit area is simply epsilon ox by T ox, and the total oxide capacitance is simply epsilon ox by T ox into area. Okay, so it would simply mean this epsilon ox is 3.9 into 8.85 into 10 raised power minus 14 into area, which is 2 into 10 raised power minus 3, divided by T ox. T ox is 55 nanometer, 55 into 10 raised power minus 9 meter, or 10 raised power minus 7 centimeter. Okay, it would come out to be equal to, let's solve for this. It is 3.9 into 8.85 into 2 divided by 55. It is 1.26. It is 1.26 into 10 raised power minus 10. Okay, or we need to find it in picofarad. Okay, so it is approximately 126 picofarad. Okay, so option A seems to be the correct option, so we will go with the option A. So I guess that's it for today, uh, and we will not be solving any more numerical questions. I would like to hear from you. So if you have any questions, you can ask one by one, so that we can try to answer those queries at this moment. And if we are having no queries, we can end the session. But let us wait. If you have any queries, you can please unmute yourself and ask the questions. Okay, yes, I forgot that problem. I had that problem somewhere. Yes, yes. Sorry, I went, I went into the mosque app directly. I had the plan to study, or to what we can say, to teach this deep depletion. That's why I went this far in the mosque app, and then I forgot. Okay. Deep depletion. Yes, this is our problem. This is our main problem. That was the first problem of this assignment. So it said that we have this ideal mouse cap, which is subjected to this CV measurement, and we are having this, what we can say, a fast DC sweep and a high frequency small signal. So we have been told to look into this, what we can CV curve, and we have been told to find whether this curve looks like since we know that this curve, we have seen this kind of a behavior previously and this kind of behavior as well, but this third kind of behavior that is depicted in this problem over here is that we have not seen it till now. What is the reason behind this kind of a behavior? So basically, this whenever we are having this high frequency and low frequency kind of a things, we do this linear ramping of the voltages. Okay, we do this linear. We do this quasi-static kind of a measurement, which is slow. We which is typically this we change the DC biases, this voltage ramps by the what you can say typical of let's say 50 millivolts for example per second. So in order to confirm, or in order to get insights into this kind of a behavior which is shown by this curve 3, which is also known by the name of this deep depletion, as rightly pointed out by the Mr. Okay, I should check who asked this question. Mr. Vinod Kumar Jha. Okay, thank you, Mr. Vinod, for this. So basically, this this ramping of this for this CV measurement, most of the times this DC voltage is ramped. Basically, ramp, like for example linear line, it is for example ramp look like this. Okay, if this is for example some x axis, this y axis, and we are doing some ramp kind of a thing, we are ramping in this case DC voltage from the accumulation to inversion. Okay, so there can be different ramping rates for this what you can say this DC bias. We can increase the slope of this thing, we can decrease the slope of this thing. So at this slowest, if we consider some slow ramping rate, and we try to apply this AC signal, we will be able to get the characteristic which will be, for example, more like first case or second case. Now, if this ramping voltage in this accumulation or depletion region, since it involves mostly this what we can say majority carriers, this this DC concentration inside this structure will change rapidly in those cases. But for this inversion case, as this ramping changes from the depletion, as we are transitioning from the depletion to the inversion region, there will not be significant number of these carriers that we will be requiring for this inversion. Okay, so this since this is the minority carriers that have to respond to the DC bias, which is ramping very fast. We need large number of minority carriers in that particular scenario, but because we are having these minority carriers that need to respond to the large ramping slope, so this means that we are requiring the significant or large number of minority carriers to attain this what we can say this charge redistribution within this MOSFET structure. Since these minority carriers are not present in that much high number, we cannot get this much amount of charge carriers by just this inversion kind of a thing. Hence, since this generation process, as we know, this generation process is very sluggish. In case of MOSFET, it is very slow. So this minority carriers are not able to respond. So as a result of this thing, in order to respond to the gate bias change, we need to reflect this thing in our semiconductor. We need to have the charge balance in the structure, and as a result of this thing, the depletion charge comes into the picture. Depletion width increases. Okay, as a result of this thing, we will be having the charge balance completely, and this depletion width will increase, as a result of which you see this capacitance is now decreasing over here. And this condition which occurs due to this what you can say fast ramping of the DC voltage is known by the name of deep depletion, which is basically due to the minority carrier concentration which is not able to respond to the gate bias changes. Okay, as a result of this thing, we are having this a depletion charges, depletion region, which increases, thereby uncovering more for example this more more what we can say charge centers, as a result of which the charge balance occurs and we get the overall charge neutrality kind of a thing. So this results in the deep depletion and results in the decrease in the capacitance since this value has increased. So I hope that this answers the question, because it is simply this decrease in capacitance has occurred because we have increased the ramp rate of this DC voltage, and this all has happened because the minority carriers are not able to respond to our ramp as quickly as the ramp is changing. Ramp is changing pretty fast for this DC bias. So this results in the increase in the depletion width, and as a result of this thing, since we are having this lesser number of minority carriers, we will be needing some charge balancing to occur, and the depletion rate increases. This results in the charge balancing act of ours what you can say MOSFET structure. So I hope that we have answered this question, and this deep depletion, this option C is what should we select for this kind of a thing. Okay, so basically it was associated with the ramping of the DC signal. We were not able to have that much amount of minority carriers, and the depletion charges, uncovering of the depletion region helped us to encounter for the charge balance in the device. Okay, Mr. Manoj. Okay, I guess you have said, you have mentioned, Mr. Vinod has left. So I guess that that's it for today. So let's end today's session. Thank you for joining.